Yep, cams on everyone. Let's start off. So last class we were doing the energy density. Great. Others, cams on? Next thing, spherical capacitors. So spherical capacitors, right? These are constructed by concentric shells. So this is how what we do. We take a concentric shell and we take another shell. And let's say both are connected by a battery of voltage V. This gets a plus Q charge and this gets a minus Q charge. This inner radius is R1 and the outer radius is R2. So if you take the field between the things, between the shells, it will be KQ by small r, for small r between R2 to R1. Because there will be no field inside the R1, there will be no field outside again. So this is the field, and we can write the potential difference, V plus minus V minus is integral E dot dr. This would be integral KQ by r square dr. Limits will go from R1 to R2 because you took plus as the upper limit and the lower as this thing. So this will give you the potential difference V is equal to KQ 1 by R1 by 1 by R2. You can rearrange this to Q by V. This turns out to be 4 pi epsilon 1 by R1 by 1 by R2. This is the capacitance. Again, derivation is really not that important, but look at the result. Let me put in the next page. Clear with this? So there, you can remember this result. So if you have two shells, R1 and R2. Now, again, understand when someone says capacitance, what is capacitance exactly? Is it the shells? The space between the shells, if you see the plus Q to minus Q, the field lines are going like this. So the space between the shells is a capacitor. The capacitance value is given by 4 pi epsilon 1 by R1 by 1 by R2. If you simplify this, you end up with 4 pi epsilon R1 R2 by R2 minus R1. Now, and what about the energy stored here? You can use all the regular formulas. So energy stored is nothing but Q square by 2C. That formula is still valid. This is the formula for a spherical capacitor. Now in this, there is a variation. If R2 tends to infinity, means it becomes a single shell. Means we got a single shell. R1, the second shell is at infinity. So you're treating infinity as a second shell. And for this thing, the capacitance would be 4 pi epsilon R1. And you can see something here, interestingly, if this thing has a charge plus Q, the energy stored is Q square by 2C, which is Q square by 2 4 pi epsilon R, and that is nothing but KQ square by 2R, self energy. Again, this is the same thing which we kept on saying. When you set the self energy, or when you say energy of the capacitor, the energy is not on the shell, it is in the form of field lines from R to infinity. So in this case, we assume the second shell it is infinity. So this is the self energy there. Have a look at this. This is the result for a single shell. There, you need to mock up these results though. Clear? Now let's see a question based on this. Turn in the page. Let's say we have a shell. We have one more shell. Radius is R. The radius is 2R. This thing has a charge plus 2Q. This thing has a charge minus Q. This is a switch and this is the earthing there. Find the heat produced when the switch is closed. Now, these kind of questions in Gauss law, we did using, remember, self-energy and interactional energy. If you remember, you get different distributions. We did it with self-energy and interaction energy. This will be much faster. Let's give it a try. Find the heat produced when the switch is closed. How do we approach this? So, Ishan, what time you reached home that day? Ishant was
Sir,
non-stop eating
around
only till 10
12:10.
o'clock, one after another, one after another. He's like, sir, cake बहुत अच्छा है. He's not leaving only the cake.
Sir, I wanted to have the eclairs. उन्होंने वापस नहीं की वो stock.
Nay, what happened? That guy was saying normally people who come there, they take one slice, right? And maximum two slices. So they have only like the same cake, they make only three cakes itself. अभी उनको क्या पता है ना, this many kids are coming and attacking. So I told them, yeah, this many kids are coming, so what did you expect? They will finish off all your cakes. So he said, sir, we made a cake, they ate it. We made a backup cake, they ate it. They ate the backup ka backup cake also, खत्म कर लिया. I
तो
said,
वो जो
good,
लास्ट
yeah.
पीस चाहिए था मुझे, इट वाज फॉलन ऑन द टेबल। आई
Okay.
केम टू गेट इट एंड देन
वो
दे नेवर
फाइटिंग में
रिटर्न्ड
चला
इट।
गया होगा. He made some other cake, but I think by then already people finished everything. So,
या हम लोग जब गए थे वो लेने डेजर्ट्स, इट वाज हाफ डन।
that is the reason if you see, you should start with the desserts.
उत्सव का आइडिया था वो।
हाँ, we should have listened
आई
to
डिडंट
her.
फॉलो
ठीक है, next time, next time.
श्योर सर।
How to do this thing? See, first let's find the charge distribution. Before the switch is closed, what is the charge distribution? This is plus 2q, inside is 0. So this is minus 2q, this is plus q. Agreed? This is the charge distribution before the switch is closed. Now understand one thing. This region between them, this is one capacitor. The region outside is a second capacitor. I can treat this as two capacitors. So the field lines are going from here to here. That is one capacitance. This is another capacitance, this thing. So C1 is capacitance between R and 2R. Again, you need to understand capacitance is nothing but the space between them. C2 is the capacitance from R to infinity to R to infinity. So C1 ka value is 4 pi epsilon R1 R2 by R2 minus R1. This is 8 pi epsilon R. C2 is a single shell, 4 pi epsilon 2R. Both are equal in this case. So the initial energy of the system is the charge 2q whole square by 2c1 and q square by 2c2. This was the energy. And if you remember this in Gauss law, this is actually equal to, if you try to calculate this, we get 3 self energies and 3 interaction energies here. So this energy actually contains, this is a combination of 3 self energies, k 2q whole square by 2 times 2r plus k minus 2q whole square by 2 times r, 2 times 2r plus k q square by 2 times 2r. These are self energies plus the interactional energy k 2q minus 2q 2r plus 2q q by 2r plus k minus 2q q by 2r. So these are interactions, meaning, can you see how big it is? Meaning you're finding interaction between these two, interaction between these two, and interaction between these two. So there are 3 interaction energies and 3 self energies. Now, instead of doing this much, you can directly treat them as 2 capacitors and finish it off. You'll get the same answer. So that entire sum turns out to be this. You guys remember something like this we did in capacitor Gauss law? The energy of a system. Capacitors is the fastest way and safer. You won't do any mistakes. There's a good chance you might goof up something. Then question still not over. Now you're earthing it. The moment you earth this charge will be gone. We don't know what the charge. This is Q. This is minus Q. This should be Q minus capital Q because the charge on the outside shell is still conserved. Now, if you take this point here, A, the potential at A should be KQ by R minus KQ by 2R plus KQ minus Q by 2R should be equal to 0. This would be Q is equal to Q by 2. We got the charge. So what is the U final energy? Again, same story, Q square by 2C1, that's one capacitor, Q minus capital Q whole square by 2C2. This is the final energy. Therefore, heat produced would be U initial minus U final. It's a pretty good question. Gauss law plus capacitors. If you try to do the self energy, it becomes, you can do it, but it becomes pretty long. Six terms you have to calculate every time. But if you treat that inner shell and the outer shell as one capacitor C1 and C2 is the second capacitor, then you can just find the energy and then you're done. Do have a look at this. So charge distribution comes from, saying the potential at the shell is 0 because you're grounding it. Is this clear, everyone? Quite a good question. So do keep this in mind. This is how you can do them instead of using the self energies and interaction energies. Saves you a lot of time and the chances of doing mistakes. Next one. Any doubts on this? Next one. So we have a hollow shell, R1. We have another hollow shell, R2. Both are connected by a battery of voltage V. The distance from center to center is L. L is much, much greater than R1 and R2. So you can treat them as they're pretty far. These are hollow conducting shells. Clear? So the first thing is find capacitance of the system. How do we approach this? See, again, if you go back to the basic how we used to derive, let the charge be plus q on this and let this charge be minus q. Now, this is including everything, okay? And since they're very far, we can assume they're not inducing any charges on each other. So this shell, which I'm taking as positive shell, so V plus would be, remember this radius is R1, so KQ by R1, potential due to your own shell. And this guy, if you look at the distance from here, minus KQ by L minus R. L minus R. You wanted this distance actually. We are finding the potential due to this at this center. This distance is, I took that as L only, not directly anyways. Yeah, so that's KQ by L. Similarly, the potential on the negative terminal will be KQ by R2 and minus KQ by L. And if you look at the potential difference, so V plus minus V minus, that KQ by L ka term will cancel off. You end up with KQ by R1 plus minus KQ by R2. I put a mistake here. This is a minus sign here. And this was a plus sign. Basically, you have to find the potential on this due to yourself and due to the other guy. Now, when I subtract them, this would be plus, and this would be minus 2KQ by L. We can neglect this since L is much, much greater than R1 and R2. So there we got the potential difference V, and we have Q 1 by R1 plus 1 by R2. So capacitance would be Q by V, which is 4 pi epsilon 1 by R1 plus 1 by R2. That's your capacitance, everyone. Check it out. माइनस नहीं आएगा. Clear? But there's much faster way to do this thing. Look at the alternate one. Now this we still didn't do, but when you take this capacitance, R1, so this capacitance is C1, so this is between infinity. This guy is R2, this capacitance is C2 between these two and infinity, and you're connecting a battery between them. This thing becomes something similar like this. You have a battery here, voltage V, you are connecting a capacitor C1, and this side is connected to the infinity. I'll just call this as infinity. And this side, you're connecting one more capacitor, C2, and this is connected to infinity, isn't it? And both the capacitors are in series. I still didn't teach you this, but capacitors in series is 1 by C equivalent is 1 by C1 plus 1 by C2. It is a reverse of resistors. You get the same answer. So C1 will be how much here? 1 by 4 by epsilon R1 by 1 by 4 by epsilon R2. This is a much faster way if you don't want to do all this potential and all this stuff. You can just treat them as two capacitors. The capacitor is connected between infinity and C1, infinity and C2, and there's a battery between them. So the infinity is acting like a common terminal for both of them. So this thing simply looks like two capacitors in series. This is a much faster way to do. Is this clear, everyone? So can you tell me what will be the answer for this guy then? Suppose if I take like this shell, we have one more shell. Let's say you connect a battery between this and the ground. Now can you tell me what will be the potential now? If you have two concentric shells like this and you put the battery inside, now what is the capacitance? So idea ये था. Basically, this ground, the potential of V ground is zero. V infinity is also zero. So this capacitance is C1, this capacitance is C2. This can be treated as we got a battery which is grounded to zero potential, and we have a capacitor C1, we have capacitor C2, both are in series, and again grounded to V infinity. Both are zero, so you can just close them like this.
So how will they be in series? Both the
Because they have the
capacitors,
same charge.
both C1 and C2
Plus Q,
are
minus Q,
capacitors to
plus
the
Q.
ground now.
कहाँ
We
पे
can
ground
go.
है?
So e- the C1 is to the ground, which is also zero, and C2.
C1, where is it to the ground? C1 is to the battery.
It's okay.
Are you
समझा.
getting this thing? Everyone terminals कैसा है? This would be the ground का terminal. This would be the infinity का terminal. But infinity is also potential zero only. So basically, you can just close the ground and the infinity together. So this would be two capacitors in series. Is this making sense, everyone? You can always treat this thing like this. Potential of A and B will be same. What is A and B here, Swastika? The shells. No, no. Why will the potentials be same? Look at this thing. There's a battery here, isn't it? So if this is zero, this potential is V. The outside cell ka potential we don't know. Is that making sense? So there are like two capacitors here. There's one capacitor and one capacitor here. Confused. Potential. I'm not. See, potential will be same if I close them with a wire, isn't it? Here, where is the wire? Wire I'm saying is the ground and infinity are same. I'm not saying the shells are same. Is that clear? Is this clear, everyone? This is a much faster way to do. You can just treat the infinity as a common terminal and then you can just connect them. So here also you can do the same thing. You can say infinity and the ground are common terminals. So basically you're connecting these two like this. And the two capacitors are in the middle. Is this logic making sense? This would give you answers faster. Clear? Going ahead. Clear, na? Vartika, Udayan, Vidyut, got this thing? Swastika, clear, na? No? Great. Next thing, cylindrical capacitors. So in cylindrical capacitors, we take coaxial cylinders. R1, R2. The length is L. L is much, much greater than R1, R2. You want them like infinite cylinders basically. Yeah, again, the same idea. We'll put a battery between the inside and outside. We'll just put on the thing there. So we will get a charge density here plus lambda. We'll get a charge density minus lambda. The field between them is given by 2k lambda by small r for r less than R2 to R1. V plus minus V minus is equal to minus 2k lambda by r dr. Limits will go from R2 to R1. So we get potential difference is equal to 2k lambda ln R2 by R1. So we can get lambda as Q by L. So you end up with Q by this is equal to 2 pi epsilon L by ln R2 by R1. So this is simply capacitance per unit length. So C by L. So for cylinders, right, we take capacitance per unit length. If you take infinite cylinder, you get infinite capacitance. You don't have much of formulas on this. That's it. Out of all, right, the parallel plate is the one with the most variations, meaning more problems. Spherical is still fine. You can combine Gauss law with that. Cylindrical, there's not much. But this was a direct result in an exam like bits or something. They'll directly ask you this. There are two coaxial cylinders, R1 and R2. Find the capacitance per 1 meter length. So these are the three types of capacitors. In reality, cylindrical capacitors are what we use a lot. But while studying, we don't study this much. Everything, the formula is valid. The energy is Q squared by 2C, energy density, everything is valid. Only the force won't be valid. Force will be zero, isn't it? Symmetrical shape. There is no field inside due to one shell. The outer cylinder due to on the inner cylinder. So what we did till now is all the basics of capacitors. So parallel plate is A epsilon by D. Spherical is 4 pi epsilon R1 R2 by R2 minus R1. This is 2 pi epsilon ln R1 R2 by R1. Next thing. Combination of capacitors. Going ahead, Aditya, Ali, Anika. Now, listen to this carefully because whatever we are going to do here, every technique that you learn here is valid again in current electricity. So there we are going to skip that techniques. So whenever circuits are given, right, there are 5 ways to do this. One, series parallel, basic. Second, Wheatstone bridge. Third, we can use something called a nodal analysis, or you can call it numbering method. People call it different ways. Fourth, we use symmetries. That is the most important one. And the fifth is Kirchhoff's law. So Kirchhoff's law is like brute force. That will give you the answers, but sometimes the questions will go lengthy. So our main aim is to try to solve with the first 4 methods: series parallel, Wheatstone, nodal analysis, symmetries. The last thing is the Kirchhoff's law. And every technique that you learn is the same technique there again in current electricity. There we will use resistors. So the first thing is series combination. So when two capacitors are in series, they have same charge and they should be in same branch. Now, before directly jumping into the formula, we need to understand something. Listen carefully here. So when you say there are two capacitor plates, C1 and C2, and this is what we say, a charge Q is flowing to the plate. Now understand this thing. When a charge Q is going to the plate, this will be plus Q here. Now this charge in reality never goes from here to here because there is a empty space between them. But the moment you get a plus Q charge here, you induce a minus Q. Are you getting this? you induce an opposite charge on the facing plate, and to conserve charge, if this is minus q, meaning plus q has gone this way, this will become plus q. This will induce a minus charge again, minus q, and again this will be a plus q flowing there. Now, did you notice what happened here? This gives you an illusion as if this is the same charge which is flowing through the capacitors. The charge will never cross the capacitor ka plates because there's an empty space in between. So what is happening is every time the charge comes to the plate, it induces an opposite charge on the other plate, and that gives an illusion the charge is actually flowing. Think of this like a relay race. Imagine if there are four twins and all are in the relay race. This person comes running here, he stops, he hands over that, whatever is that, and then he runs, he hands it over, he runs. But for a person seeing from outside, it feels the same person is running throughout the entire race. So this is one thing important. So whenever someone says a charge is flowing, through the capacitor, the reality, the charge never flows through the capacitor. What you're doing is inducing the charge on the other plate, which gives you an illusion the charge is flowing. This is one thing which you should be clear. So charge on the positive plate induces minus q on the facing plate, right? And plus q goes ahead. Because you're getting a minus q, the total thing should be zero because it is neutral. Right? So it feels as if the same charge is flowing through the capacitors. So be careful here. Charge will never jump across the plates. If someone asks you this question, how much charge is flowing between the plates? Zero. The charge will never flow through that. It is just our illusion. It gives you a feeling as if it is going. I hope this part is clear, everyone. This is how charge goes through capacitors. So we want to replace these two with a single capacitor, C equivalent, with a charge Q. So basically the potential difference between these two should be same. So V1 plus V2 should be equal to V equivalent. Potential is V1, potential is V2. Q by C1, Q by C2 is Q by C equivalent. There, this formula is reverse of resistors. And since both of them have same charge, Q is equal to C1 V1, C2 V2. So the potential will divide in the ratio of opposite resistances, capacitances. So in series, this is the formula. And this is the relation between the potential differences. V1 and V2 are potential difference across the capacitors. There, have a look at this.
सर
Yeah.
So sir, I mean, अगर वो माइनस क्यू के कारण द प्लस क्यू गोज इन द आगे वाले प्लेट में, तो क्या वो फर्स्ट प्लेट के माइनस क्यू से एंड सेकंड प्लेट के प्लस क्यू के बीच में does the battery not do work?
Where is the battery here?
If there's a battery, if there's a battery.
It will do work.
So but वो जो माइनस क्यू से प्लस क्यू वाली प्लेट के बीच में जो चार्ज गया है वो तो लाइक जो इंड्यूस हुआ था उसके कारण गया ना.
But first of all, where did you get that plus Q from?
So नहीं वहां तक बैटरी ने वर्क किया, मतलब लाइक उस प्लेट की लाइक इस प्लस क्यू प्लेट तक लाने के लिए, लाइक उसके आगे फिर वो वर्क करेगी क्या?
It is nothing like, see, you're thinking it'll just push and leave it. It doesn't do that. What did I tell you last time? What is a battery like? Battery is like a machine which is running a conveyor belt. So do you mean to say when the battery is pushing the conveyor belt, it only pushes one part? The whole belt starts moving at the same time. It's not like only left side charge move karega, the right wala charge wait kar rahi, charge aayega, then I will go. The whole thing will go at the same time. So whenever you think about a battery, don't think of it like something just pushing once and done. It's like a whole conveyor belt. The charges are there, and you're pushing all of them at the same time. Meaning the moment you get plus Q here, at the same time you'll get this minus Q. SNI, there's a delay between them. All got this? Next thing, parallel. They have same potential difference. And they're connected across the same nodes. What are nodes? Nodes are nothing but the point where the two branches meet. So if you have something like this is a node, point where branches meet. So if you have a capacitor like this, C1 and C2. You want to replace this with one single capacitor, C equivalent. So if you say charge Q is flowing here, let this be Q1 and this be Q2. So we have Q is equal to Q1 plus Q2. So this would be C equivalent into V. This would be C1 V plus C2 V because all have same potential difference. So C equivalent is C1 plus C2. And what about the charge? Q1 is C1V, Q2 is C2V. So the charge divides in the ratio of capacitance. So more capacitance, more charge you get. There. We are just playing with Q is equal to CV only. So the formulas are completely opposite of resistors. So be careful with that. Clear? Next one. Previous page here. So series parallel is fine, but main thing is like how the charge flows. So be careful with that. In a capacitor charge, reality may never flows. It's just being induced. Clear? Next one. Then Wheatstone bridge. We have done all this stuff. We have done this in heat transfer. Then we have done this in viscosity, Poiseuille's equation. This is the third time you're handling all this stuff. The Wheatstone bridge, what it says. C1, C2, C3, C4, and C5. So if C1 by C3 becomes equal to C2 by C4, then C5 can be removed. you can have an extended Wheatstone bridge. You have a capacitors. C1, C2, C3, C4, C5, C6, C7, and C8. If the ratio C1 is to C2 is to C3 becomes equal to C4 is to C5 is to C6. Basically, this forms a Wheatstone, this forms a Wheatstone. All the ratios should maintain. If only this ratio is managed and this ratio is not managing, even you can't remove C7 also. If this everything manages C6, then C7 and C8 can be removed. Let's say you just satisfy C1 by C2 and C4 by C5. You can't even remove C7. That is because you didn't satisfy the C8 ka condition. So this capacitance ka value itself will change. So an extended Wheatstone bridge, you can put 10 junctions. It doesn't matter. You can remove all of the things in the middle, but that ratio should be manageable. We can call this extended Wheatstone bridge. So there, parallel, series, and Wheatstone bridge. Clear? Let's see. Rehan, clear na? Adrit, Abhinav, Aditya. Great. Let's see a question. So we have a capacitor, we have a capacitor, 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 and there's a conducting wire. This is V, this is C, 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 and C. Find C equivalent and charge on each capacitor. Now again, understand when I say charge on each capacitor, I'm not talking about total charge. Total charge is 0. We're finding the charge on the inside of the positive plate. Find charge on the capacitors. Let's see how will you do this thing. Think for a minute. Then we will discuss what does that wire do exactly. Okay. Now understand. It will short circuit, yes, in this case, but let's actually try to understand what does a wire do. See, wire has a very simple purpose. A conducting wire will simply make the potential same. That's it. right? For the connected points or for the connected nodes. This is what it does. Because you will need to understand, because later on I'll show you cases where it won't get short circuited. Now here, now if the wire is across an element, now that element can be resistor, can be capacitor, can be inductor, anything. Meaning if you have like this, so what you did is you made this point A, so this point is also A. So basically both the points are same potential. So potential difference is 0. Therefore, capacitor can be removed. So this is what we call as shorting. You'll understand the importance of this later on. Getting it? So basically, this is short circuit. So we'll say the element is shorted or something like this. This is the meaning of this. Now, why am I saying this specifically? For example, see, suppose if I have something like this. Now, can you still remove the capacitor? Now, can you remove the capacitor? Now you can't do, right? So why go wrong? So we have to be careful because, I don't want you to get a feeling like, if I put a wire, I can remove anything. When you put a wire, it makes the potential same. In this process, if the potential difference becomes 0, you can remove it. So in our question, so this thing, this guy can be removed. Circuit simply becomes like this. Find the capacitance. So how much is this? C and C. This guy will be 2C. Be careful here. This is 2C. The other three capacitors are in series. So that can be written as C by 3. And this is 2C and both are in series again. So C equivalent would be 2C into C by 3 by 2C plus C by 3. C1, C2 by C1 plus C2. This turns out to be 2C by 7. So therefore, the charge flowing through the capacitor is 2CV by 7. So from here, charge Q will go. So this will get plus Q. I'm not writing the negative plate ka charge. So this will be plus Q. Then this will go plus Q. This will split Q by 2, Q by 2. This guy will get taken Q back and you're done. Q comes back and the other one is 0. Easy. So there, in this question, the main thing is if you put a wire, what happens? Potential becomes same. That's it. If someone asks you what happens if you put a wire, always say the potential becomes same. Don't say shorting. Because we will see cases where you can't remove the element even if you have a wire. Any doubts on this? Going ahead, let's see something slightly more complex. Clear, na? Vartika, Swastika, got this? Vidyut, Neil, clear? Going ahead. This is C, 2C, 2C, and C. We have a switch in the middle. This is connected to a battery. Find the heat produced. Let me ask you like this thing. Find C equivalent before and after closing the switch. Find charge flown through the battery and heat produced when switch is closed. Meaning exam method directly asks you to find heat produced. Initially switch is open. third, how much charge flows through the switch when it is closed? When you close the switch, how much charge flows through that center wire? Let's get this. Again, this is just series parallel. I didn't teach you anything big. The potential is same across. If the potential is same across Aditya, then there is no potential difference, right? V plus and V minus both are equal. So if the potential difference is zero, then what is the capacitance? Q is equal to CV. Q is zero. Remember that Q is equal to CV. V is not the voltage of the battery. V is the potential difference across the two plates. Then if there's no charge in the capacitor, it is as good as nothing. So you can remove it. Fair enough? Yeah. Yeah. Get the remaining. Get the heat produced. That is the main question. The first question capacitance I just gave like that because I thought you won't get an idea. First one is like when you go to the restaurant, you'll get that papad, no? It is that one. Try. I'll give you a minute for the first one. 3 minutes for the second and third one. It's a good one. E before 4C by 3. Okay. Heat इतना अच्छे से आ गया रे. I hope you included the work done by battery also. You did? चला अच्छा है then. Let's see. Get the third part also. Just give it a try. You did only that क्या? You forgot God. What did you write last time? Heat produced के लिए मैंने कुछ लिखा था. याद है? You have to take the initial energy and final energy also. Look at this thing. This is what I was saying. Just because you have a wire doesn't mean you can remove everything. Now, before the switch is open, the circuit looks like this. Capacitor. So the upper two are in series, the bottom two are in series, and the up and bottom are in parallel. So the C equivalent, so 2C and C are in series. So 2C by 3, 2C by 3. C equivalent is 4C by 3. So the charge that went through this thing, let's call it Q1. So Q1 is 4CV by 3. Now up and bottom are equal. So the charges will distribute 2CV by 3 and 2CV by 3. because even though they're different, this is 2C by 3, this is 2C by 3. I hope any doubts on this, please ask me. I'm directly writing the capacitances. I hope you know series parallel, so I'm doing that. So this charge would be 2CB by 3. I'll write this as simply Q1 by 2, okay? That will be Q1 by 2. Then the charge will go here. This will be Q1 by 2. This also will be Q1 by 2. This also will be Q1 by 2. If I just write the negative plate, minus Q1 by 2, minus Q1 by 2, not required, but I need it for the third problem. Minus Q1 by 2, minus Q1 by 2. There, I'm putting the negative charges with green and the positive plates with positive charge. Any doubts on this thing when the switch is open? Now, when the switch is closed, now the circuit will suddenly transform. So C, 2C, 2C, and C. So this circuit now can be written like this. Since that is a wire now, you can just join them like this. Did you see what happened? These two became parallel, these two became parallel because it's the same potential difference. Meaning if you just take this point as A, this entire point, if you see, this entire line is same actually. Let's call it B. Let's call this point C. If you look at this, the potential difference is VA minus VB. This is VA minus VB. They both are in parallel. The entire center line, you can just compress it into a single point. Is this making sense? This is what I was saying. Whenever you put a wire, it simply makes the potential same. So meaning if I call this X, this point is also X. Then the potential difference is VA minus VX and VA minus VX. And the right side of the potential is Vx minus Vb and Vx minus Vb. So this is A, this is X, and this is B. So C and 2C are in parallel, 2C are in parallel. So C equivalent will be 3C by 2. Now the charge that will flow is 3CV by 2. Any doubts on this? Please ask me. They're in parallel, right? Parallel means it is C1 plus C2. Be careful with the formula. So in the first case, when the switch is open, series, parallel. When the switch is closed, parallel, left is parallel, right is parallel, left and right are in series. Yeah, then you can be negative, there कुछ problem नहीं है. So charge that flows is Q2 here. Now charge Q2 has gone here. Now we have to be careful here. Look at this. Now C and 2C, right? Charges will distribute in the ratio of capacitance. So this guy will be Q2 by 3. This guy will be 2Q2 by 3. Then this guy will be Q2 by 3. This guy will be 2Q2 by 3. Look at the charge distributions. I'll show that here if you want. This is C. This is 2C. If you send Q2 here, if you say this charge is X and this is some Q2 minus X, then X by C, the potential difference should be equal to Q2 minus X by 2C. From here we get X is equal to Q2 by 3. Yeah, the formula is still valid. Please have a look at this. Let me show you more in this. This is the charge distributions. This should be clear to everyone. Just by closing the switch, you made the circuit into something else. Circuit completely changed. which was initially series, then parallel, no, suddenly become parallel, then series. Clear? Can I go ahead? Now let's see the questions what I asked. C equivalent to nikal diya. Now we want charge flowing through the battery. Now, initially how much charge is flowing through the battery? Q1. Now how much charge is flowing through the battery? Q2. So what was the difference? Q2 minus Q1, isn't it? Meaning already through the battery Q1 went, then Q2, this is what you're showing. So the additional charge that flowed, this is that extra charge or additional charge when the switch is closed. You need to understand that. Already Q1 chala gaya. Now you sent Q2, meaning the difference you sent is Q2 minus Q1, which is 3CV by 2 minus 4CV by 3. This guy would be CV by 6. 339 minus what? Yeah. This is the extra charge that flows through the battery when you close the switch. I hope. Is this clear? It is not Q2. You already sent some charge. What is work done by the battery? The work done by the battery is the charge that flows through the battery into the potential of the battery. Again, this is all additional charge. You need to understand. The whole question is when the switch is closed, find the heat produced. So before the switch is open, the battery did some work. I'm not interested in that. The question looks pretty simple and straightforward, but they can really play around with this. When you think like this, before the switch is open, battery gave 100 charge. After the switch was closed, the circuit में there is charge 150. So battery extra kitna diya? 50 na? It already gave 100 before. It's not like I'm giving you fresh 150 now. The question was also that only. Find the charge that flows when the switch is closed. Charge through battery into the potential difference. So this guy would be CV square by 6. So what is the heat produced? Heat produced is your initial energy plus work done by battery minus U final. So initially half capacitance is 4C by 3 V square. I can use half CV square formula. Work done by battery is CV square by 6 minus half C equivalent is 3C by 2 V square. I'm simply using half C equivalent V square, isn't it? So potential energy is nothing but half C equivalent V square. You can replace that whole thing with one single capacitor. एक एक capacitor में क्यों calculate करना है? You can replace all the 4 capacitors with one single capacitor. You'll get C equivalent. So half C equivalent into V square is the energy stored. There is no need for you to find for each capacitor. That's quite lengthy. So this would be 2CV square by 3 plus CV square by 6 minus 3CV square by 4. This would be multiply 2 and 2. This would be 5CV square by 6 minus 3CV square by 4. Numbers are not great. So 5, 4, 20 minus 18, 2 to CV square by 12. That's your heat produced. 12, na? 4 it is. Do check it out. Maybe I messed up the calculation too much. Any steps you didn't get, please ask me. I asked the work done by battery and you can't do that, Adrit. Half mat karo. Half is when only the initial the capacitor should be empty. Questions are completely different. Any doubts on this? Clear, na? Saina, Utsa, got this? Anusha, Molika, Aditya, Ali, Aryan, anyone confusions, please ask. Vartika, Vidyut, Ishan. Question abhi tak hua nahi. How much charge is flowing through the switch? Question is still not over. How much charge is flowing through the switch when you closed it? How do you do that? Try, I'll give you a minute. Let's see. Now look at this plates here. Huh? You need to understand. This is the switch, no? Just look at this guy here. What is the charge there? Minus Q1 by 2 minus plus Q1 by 2. Q1 is how much? 4 CV by 3. So the charge on this was minus 4 CV by 3. The charge on this was 4 CV by 3. This was when the switch was open. When you close the switch, and the switch is closed, now look at the charges. Now the charge was minus Q2 by 3 and plus 2 Q2 by 3. That was Q2 is how much? 3 CV by 2. So CV by 2. So on this, the charge became minus CV by 2. On this, the charge became CV. Is this making sense? These are the charges on the plate. Now tell me one thing. If you look at these plates here and the switch together, this is completely an isolated system. They're not touching anyone. Now the only way, now initially you had 0 charge. Now suddenly you have CV by 2 charge. Where did you get this from? The only way charge can flow through these two plates is through the switch, isn't it? Is that making sense? If you look at these 3 plates here, this whole system is isolated.
minus 4C by 6 होगा ना
कहाँ पे होगा? हाँ 2 CV by 3 होगा ना? Yeah.
minus Q1 by 2 था ना
Yeah. So minus 2 CV by 3, but ठीक है, luckily आंसर फिर भी आ जाता था. It is wrong though. You're getting it? That's an isolated here. So that means any charge on these two plates must have come through the switch. So what is the final charge here? So the final charge is CV by 2. Initial charge is CV. Final charge is CV by 2. Initial charge is 0. So where did you get the extra charge from? Through the switch. Therefore, charge through the switch is CV by 2 flowing upwards. Is this making sense, everyone? Because see, if you just look at all the plates, total charge is always 0, right? The charge on positive and negative plate together is always 0. So you need to ask yourself, look at these two plates here, these black plates which I'm marking here, those are the main ones. So if I mark this plate as some black color, initially the two black plates may charge is 0. Now suddenly on the two black plates, the charge is not 0. Matlab the extra charge came from somewhere. And the only way charge can come there is through the switch. Is this logic making sense, everyone? There. So this is a question based on simple series and parallel. The moment I ask you for heat produced, question becomes something else. This is what I was saying. Just because if you put a wire doesn't mean you can always remove. Things will be a little different. Clear? Next one. Next one. We have a capacitor, we have a capacitor, we have a capacitor, we have a wire going like this, and we have a wire going like this. So let's call this point B and let's call this point A, meaning battery is going to be between A and B. Find the potent capacitance across CAB. So A and B are the terminals where you're going to connect a battery. Those are conducting wires. Yeah. So let me teach you a method here. This thing we can call it numbering method, nodal analysis. So what we do in this, step 1, identify the number of nodes. And check for nodes for same potential. So generally, the biggest hint to use this is when you see a lot of conducting wires. That is the biggest hint that you have to use this. And check for nodes with same potential. Step 2, name the nodes. Maybe give them different symbols, A, B, C, D, or 1, 2, 3, 4, however you want to give. Step 3, redraw the circuit. Now, look at this thing. For example, in our question here, this point is A. So this is a node. So this is a wire, meaning this entire wire will have same potential. So this point is also A. Isn't that what a wire does? It makes the potential same everywhere. If this point is B, this is a wire. So this entire point is potential B. So even though in reality there are 4 nodes, node 1, node 2, node 3, node 4, in reality there are only 2 unique nodes or 2 same potentials. Is this clear, everyone? Then rename, put the circuit again. So there are only 2 points, A and B. Let's call this capacitor 1, capacitor 2, capacitor 3. Now capacitor 1 is between what? A and B. Capacitor 2 is also between A and B. Capacitor 3 is also between A and B. There, if you read out the circuit, you can clearly see all are in parallel, which is 3C. Is this making sense, everyone? Once you read out the circuit, it becomes simple series parallel. Let me show you one more. But this is the idea when you solve these problems. And the biggest hint is you see a lot of conducting wires. You guys try this. Find CAB. All are same capacitances. Let's get them both. This is your second technique, nodal analysis. First was series parallel. Again, remember step 1, see how many nodes are there. This is node 1, node 2, node 3, node 4. There are 4 nodes. Find how many unique nodes are there. Meaning if this is A, this entire wire will be A. Now if this is B, you're stuck. There is a capacitor here. Meaning no, that's not B, it is something else. So let's call this C. That's the idea. There should be a wire. There's no wire, na? There's a capacitor in the middle. So it is not B, it is something else. So let's call it some point C. Now, a simple thing, whenever you're redrawing the circuit, make sure, listen carefully, whenever you're doing the circuit, make sure your first terminal and the B terminal are always on the corners. Everyone else will be in the middle. Second thing, make sure the wires are not crisscrossing, okay? So if I number these capacitors, let's call this capacitor 1, capacitor 2, capacitor 3, and capacitor 4. So capacitor 1 is between A and C. Capacitor 2 is also between A and C. Capacitor 3 is between A and B. Capacitor 4 is between B and C. Now, can you see the circuit? Series parallel? This is how you do this. Please ask me if you're confused. You just need to see which points of same potential, read of the circuit and finish it off. And make sure while drawing now, wires are not going like this. You have to keep them separate. So this would be 2C, 2C and C in series 2C by 3, and this thing, C equivalent is 5C by 3. Yeah. Get the next one. Any confusion on this method, please ask. Once you read out the circuit, it suddenly becomes easy to solve. And the biggest hint or the idea is you can see wires like this, meaning you're making 2-3 points same potential. (13C by 8). Okay, let's see. We have two 13C by 8s for the third one. Let's see. Step 1, find the nodes and make them into same thing. So you're calling this is point A. So meaning this entire wire is A. You're getting? That is the meaning of the entire wire is A. If this is B, bas ho gaya. Matlab, there is no connection. So that is B only. There is no one else. Let's call this guy C and let's call this guy D. See, if there is a capacitor between 2 points, game over. The points are different. So if the point is different, just keep putting a symbol A, B, C, D. Kitna symbols aega, itna just keep putting it. So this is how we redraw. A is in the beginning, B is in the ending. Why? Because battery is between A and B, so everyone else is in the middle. Then C is somewhere here and D is somewhere here. Let's name the capacitors 1, 2, 3, 4, 5, 6. Capacitor 1 is between A and C. Capacitor 2 is also between A and C. Capacitor 3 is between C and D. Capacitor 4 is between A and D. Now, this is what I said. Make sure they're not crisscrossing. So you can clearly see their series parallel. Capacitor 5 is between D and B. Capacitor 6 is between A and B. Now, is it easy to solve? These two are in parallel 2C. These two are in series 2C by 3, 2C by 3, and C are in parallel 5C by 3, 5C by 3, and C 5C by 8, 5C by 8 plus C, 13C by 8. I hope the method is clear, everyone. Clear? Any doubts on this? Anyone confused with anything, please ask. It's important. Once you got this, it'll be easy from there. Clear? So let me ask you one more then. This is A and this is B. This is a conducting ring. Now, all are C. If I don't mention anything, take all capacitance are C only. So this is point A. That's it. There is no other A anywhere. But if this is B, this entire ring is B. Meaning this guy is B, this guy is also B, this guy is also B. This guy is neither A nor B, so this is someone else C. So basically there are three different nodes. I hope everyone is getting how am I figuring out there are three different points. Because if this is A, done, that's it. There is no other A because there's a capacitor. If this is B because it's a wire. And if this is a B and there's a capacitor, so this is gone, this is someone else. Basically there are 3 points, A, C, and B. Between A to C, there's only one capacitor. Between B to C, there are 3 capacitors. There. So C current would be 3C by 4. This is 3C, 3C, and C. So that is 3C, yeah, 3C by 4. Be careful, huh? वो series parallel का sometimes usual resistance का formulas. Got this? This, I hope the node analysis is clear. Have a look at this. Take a break, come back by 7, and we'll continue from here. The same technique we'll use in current electricity. Only thing series parallel ka formulas will be reversed. Any doubts on this nodal analysis, please ask. Take a break, come back in 10 minutes. Yeah. Chalo, comes on everyone. Let's see the next one. We have a plate. So there are 5 plates like this. The area of each plate is A. Distance between the plates is D. And then you're connecting battery between you kept the battery between these 2 plates, and you're connecting these 2 plates with a wire. You're getting it? So if I name them now, this is plate 1, plate 2, plate 3, plate 4, plate 5. So 1 and 4 का बीच में battery है, and 2 and 5 are connected by a wire. Battery का voltage is V. Find C equivalent. This is an easy one. Find charge on each face of the plate. This is a better one. Charge on each face of the plate. Meaning, understand, first plate ka there are 2 sides. First ka upper, first ka lower. Second upper, second down. Third upper, third down. Fourth up, 4 down. 5 up, 5 down. There are 10 faces. So I want charge on each face. Let's get this. Three A epsilon by D. Okay. Let it be C, na? A epsilon by D is equal to C. Start from there. I'm more interested in the charges on each face. Eight आया क्या? Try. I'll give you a minute, then I'll show you. Let's name it like this, okay? Let this point be A. Let this point be B. Normally, I take like this. I always take the positive as A and the negative as B. The battery got two terminals. If I call this point C, this also has to be C. Why? Because they both are connected with the same wire. Meaning this guy is some D. So in total, there are 4 terminals. So there's a terminal A, C, D, and V. Battery is between A and B. Now be very careful when you put the phases. Now understand here, what is a capacitor? Capacitor is nothing but the space between them. So this capacitor, the first one, is between A and C, fair enough. But it is made of which phases? So this thing is made of first plate ka downside, and this thing is second plate ka upside. Are you getting how I'm writing? 1 down and 2 up. So this first capacitor is constructed by first plate ka downside and the second plate ka upside. The second capacitor is between C and D. This is constructed by second plate ka downside and third plate ka upside. So you need to specify each one because you want charge on each face. The third capacitor is between B and D. This is constructed by third plate ka downside and fourth plate ka upside. This is constructed by B and C. So, and this is B ka downside. So this is fourth plate ka down and this is fifth plate ka up. Please check. Because this and this potential is same. So fifth plate ka up is also point C only. This classification you should do, or else you won't get what is the charge on each face. So once you got this, C equivalent is easy. This is C by 2, 3C by 2, 3C by 2C, 3C by 5. And C ka value is A epsilon by D. So 3A epsilon by 5D. Have a look at this. Now, if you look at the charge distribution, so Q is equal to 3CV by 5. So if I assume charge Q is going here, this would be plus Q. This would be minus Q. Then charge Q will continue to go. This is C and this is C by 2. So charge will split in the ratio of capacitances, they're in parallel. So this should be 2Q by 3. They'll split in 1:2 ratio. So yeah. And this will be Q by 3. And Q comes out again. So this is plus Q. This is minus Q. This is Q by 3. This is minus Q by 3. This is Q by 3. This is minus Q by 3. This is 2Q by 3. And that is minus 2Q by 3. There, charge on each face. Now, exam they'll ask you find the charge on the second plate. What will you write? Charge on the second plate is 2 up and 2 down, na? That is minus Q and plus Q by 3. Minus 2Q by 3 is the answer. You're getting, you'll be trapped like that. If they ask you charge on the second plate, third plate, you won't be able to solve without knowing what the charge on each face. So if they ask you charge on third plate or second plate, basically you should take the charge on 2 up and charge on 2 down. That would be minus Q plus Q by 3. Minus 2Q by 3 is the charge on the second plate. I can ask this also. Find the charge on the third plate ka upper side. Please have a look at the distribution. So when you rename the capacitors, just be careful which sides are you using to make a capacitor. So the first capacitor is due to 1 down and 2 up. This is 2 down, 3 up, 3 down, 4 up, 4 down, 5 up. Is this clear, everyone? If you just want to find C equivalent, na, itna karne ka zarurat nahi tha, meaning you would have got easily without all the symbols. Because the moment I ask you charge on the plate, you're done. You have to do this. You don't have an option. Any doubts on this? Please ask me. Next one. Anika, clear with this? Adrit, Aryan, Malika, Rehan? Clear, na, Ishan?
Yes, sir. Just एक question था. If a plate is isolated, for example, इसमें third वाला, in
तो
that
zero
case
होगा
charge
ना
is
charge.
obviously zero, ना?
3 up, 3 down, देखो ना, 0 आ रहा है.
Yeah.
No. The middle, in the middle, na, the wire is jumping over it. They're not crossing each other. Get them. All capacitance are C. Find CAB in both the cases. Right, Swastika. See, if you look at this, if you try to apply nodal analysis, you'll realize this point is C, this point is D, all points are different. Nothing, meaning there's no use actually. Like I said, nodal analysis is useful if you can eliminate at least 1 or 2 nodes. They should have same thing. Here, nothing is looking same. So, but if you can observe clearly, right, you'll notice something there. It's a hidden Wheatstone bridge. So if you just put this thing, there's one capacitor between A and C. There's one capacitor between C and D. There's one capacitor between D and B. There's one capacitor between these two, and there's one capacitor between these two. I'll name them for you. This is capacitor 1, 2, 3, 4, and 5. So this is capacitor 1, and D ka capacitor is 4. This is 2. This is 3 and this is 5. So capacitor 2 can be removed. It's a Wheatstone bridge. So the circuit simply becomes like this. So therefore CAB is equal to C. 14th, next B is something similar. Yeah, there's a difference. This is a Wheatstone bridge. This is your third method, third case. Like I said, series parallel, nodal analysis, Wheatstone bridge. So whenever you see a circuit, generally you try to go in an order. Okay, is this series parallel? Can I use nodal analysis? Does this look like Wheatstone? Then we'll say, does this have a symmetry? Nothing is there. Then chupcha we use Kirchhoff's law. That is the last thing you want to do. What about this guy? Again, same story. Let this be C, let this be D. So A, C, D, and B. You will notice there is one capacitor here, capacitor here, capacitor here, capacitor here, capacitor here. On top of it, there is one capacitor outside A and B. So this is a Wheatstone bridge with a capacitor in parallel. So when you draw, just make sure the capacitors are not crossing over each other. So this CAB will be 2C. This is also Wheatstone. You can remove the middle one. So this circuit, if you redraw, it looks like this. So you can always redraw a circuit, meaning you can put however you want. Yeah. So it's a Wheatstone in parallel with this. So Wheatstone is pretty standard. There's not much. Next one. Any doubts on this, please ask me. So basically this guy can be removed C and D. Turning the page. Clear, na? Neil, Malika, Vartika, got this? This is a good one. We got a cube here. A, B, C, D, E, F, G, and H. 4 points are there. Each wire has a capacitor. To total 12 capacitors. All are C. So find CAG, means if you put the battery between this guy and this guy, find the equivalent. Find CAB, find CAC. There's 3 different questions. Means connect the battery between A and G, find the answer. Find the battery between A and B, find the answer. A and C, find the answer. These are the 3 different possibilities in a cube. You can't do anything more in this. And all are C. This is a cube symmetry. Now we started with the 4th one, the symmetries. Symmetries, there are more cases. This is a one kind of symmetry, cube symmetry. Then we have infinite grids. Then we have axial symmetry, bisector symmetry. Then we have diagonal symmetry. We have a lot of things. Let's see. Let's do for AG first. Give it a try. Take a minute or two, then I'll show you. If the battery is between A and G, 6c by 5, 9c by 2. Let's say I don't remember the answer actually. No. Look at this. When you're going in a cube, ask yourself, it is like this. You want to go from A to G, isn't it? The charge is trying to go from A to G. You can see by symmetry, point B, point D, and point E are identical. If you think about it, see, for every path that you show through B, if you say I'm going A, B, C, G, I can show you an identical path through D also, A, D, F, G, A, E, F, G. See, that is the meaning of symmetry. When you say I'm going from A to G, for every path that you take through B, I can show you a similar path through D and similar path through E. That means if I erase these symbols D, B, and E, and if I rotate this cube, you can't tell who is which point. Isn't making sense? So, for every path from A to G through B, there is a similar path through D and D. Meaning, if you just think about it like traffic, right? If you're sending, let's say, like 30,000 cars, and if all three paths are identical, you can be pretty sure that each path will have 10,000 cars. Sample should be big. If you say only 2 cars, so then it will be a problem. So when you have a large sample, right, you can see by symmetry, all will take equal paths because all three paths are identical. Therefore, B, D, and E have same potential. That much I know. Now, if some points have same potential, meaning you can use nodal analysis. Similarly, you can argue the same way from reverse. Similarly, C, H, F have same potential. So this point, and this point. So in reality, there are only actually 4 different potentials. So this is point A, this is point B, this is point B, D, E. All three are there together. This guy is C, H, F. Now look at this thing. From A to B, there is one capacitor. I'm just drawing one line. A to D, there is one capacitor. A to E, there is one capacitor. There are 3 of them. B to C, B to H, there are 2 capacitors. D to C, D to F, there are 2 more capacitors. E to F, E to H, there are 2 more capacitors. And here there are 3 capacitors. They got 12 capacitors, 12 lines. Circuit has simply become series and parallel. So this thing will be 3C, this thing will be 6C, this thing will be 3C. All 3 are in series. So CAG, sorry, this is G, will be how much? 6 into, that would be 3 by 2 by 6 plus 3 by 2. 6C by 5. Please check it out. That cube suddenly becomes into series parallel circuit. So there, we are using cube symmetry in combination with nodal analysis. So the main idea in the cube is that the 3 points have same potential when you go from A to G. Anyone not convinced with this, not clear with this other, please ask me. It's quite a good one. This is what I mean by symmetries. If you can argue and you say 2 points are identical in every respect, then you can say both have same potential. If they have same potential, you can join them into a single point. Redraw the circuit, life becomes easy. If you can, moment you can combine 2 to 3 points, circuit becomes pretty simplified every time. If this is clear, can you go for A to B? Now again, same logic. I'm going from A to B, find the symmetrical points. So depending on you're going from where to where, the symmetrical points will change.
Then what were the other two subparts?
A, B, na? A, B, A, C.
See.
A, B. Next one is C, A, B. Meaning you're keeping the battery here and here. Let's get this, everyone. 15C by 11, I don't think so. 11 तो नहीं आएगा, इतना याद है मुझे. Try. Again, what I am doing here, exact same things we can do in current. So we are going to skip all these things there. To C, 15C by 8. Okay. Again, the same argument. You are traveling from A to B. Okay. When you travel from A to B, you can see for every path through D, you can find a similar path through E. See, if you go from D, AD, CB, 3 capacitors. AE, HB, 3 capacitors. They look quite similar. You show me any path through D, I'll show you same path through E. So we can say D and E are same. Similarly, by argument, you can also say C and H are same. Just remove that green line. C and H are identical. This color is not looking good. C and H are identical. F and G, they are nothing. So you can see here D and E are identical. So there is no mathematical proof. You have to just argue with that thing saying symmetry. Means if I just erase D and E and if I rotate them, you can't tell who is what. Similarly, C and H are identical. F and G are not same. Because see, when you try to go from A to B, A, E, F, F comes second, A, E, F, G, G comes third. They're not symmetrical. So redraw the circuit, point A, then we have D and E together. Out of all, this is the most complex one. Then we have F, then we have G, then we have C and H together, and then we have B. We couldn't remove many points. So between A to D, D to E, 2 capacitors, D to F, E to F, 2 capacitors, F to G, 1, G to C, G to H, this is 2. And then we have from D to C, and then we also have E to H, and then we also have this. But still you can handle this, series parallel. Have a look at this. And if I put one more line like this and put a horn like this, it looks like some kind of monster, but yeah, that's all the circuit. Please check the circuit. This is how the circuit would look after simplifying. You have only 2 common terminals, D and E and C and H. How much is this? This is 2C, 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 C, C, and again that is C by 2. C by 2, CC, 5C by 2, 5C by 2, Phi C by 2, and this is 2C, C. Phi C by 2, C would be Phi C by 7. Phi C by 7 plus C would be 12C by 7. Check, anyone got this? Please ask me if you're confused with the circuit. Once you read out the circuit, then it is simple series parallel. This thing in the middle, parallel, this entire center is series. This is parallel, this is series, and this is again parallel. Circuit gets over, series, parallel, series, parallel. The main thing is to figure out that D and D are same and C and H are same. Question still not over. We have one more, C, A to C. This time you are going from A to C. The battery is between A and C. Ishan nahi re, bahut acha answer aayega re. What did I say just now? The second is the most dangerous one. Third is pretty neat actually. Let's see. A to C, everyone. This is cube symmetry. There's one more type of symmetry that is there, we can call it, but let's see. Yeah, right, Utsa. Actually, now all four are same. If you look at this cube here, if I take this thing now, middle plane, there's another name for this called actual symmetry, we'll see that. But if you look at the plane in the middle, yeah, this red one's not irritating actually. Let me remove them. So you want between C and this thing. Now, if you take the central plane, if you look at this thing here, all these four are midpoints, isn't it? When you go from A to C, A, E, F, G, C, F is the midpoint. A, E, H, G, C, H is the midpoint. A, D, C, D is the midpoint. A, B, C, B is the midpoint. And the left and right are symmetrical. Means what? All these points have same potential, isn't it? The entire plane in the middle is equipotential. Because those are all our midpoints. If you see here, the plane D, F, H, B, right, is a symmetrical plane. Meaning, if you see A and C are mirror images. Basically, you can say for every path A to C, these points are midpoints. D, F, H, B are midpoints. Therefore, we can say potential will be half of it, or V by 2. Meaning, I'm assuming C is 0 and A is V. So therefore, all the 4 points are identical. So what we can do? We can remove anything between them, isn't it? If all have same potential, we can remove simply any capacitors between them. बस circuit ऐसा हो जाएगा ना. You can remove this guy and you can remove this guy because they are the same potential. If F and D have same potential, you can remove that. H and B have same potential, you can remove that. Is this making sense, everyone? Why couldn't we do this for the previous one? This one, there is a symmetry, but what is the use? Na? There is nothing anywhere in the middle. There was no use. Why couldn't we do here? That's not symmetrical. See, you can't draw a diagonal like this. A and G are not mirror images. Cube is not symmetrical about the body diagonal. So then you're done. So what is the answer for this? These two are in series. These two are in series. These two in series. These two in series. These two are in parallel. So that would be C by 3 and C by 3. Is this clear, everyone? So basically the 4 points, B, D, H, F, 4 points are identical. Clear? Any doubts on this? This is how you play with a cube. Nodal analysis and cube ka symmetry. Next one. Any doubts? Anika, got this? Clear, na? Rehan, Palaksh? Clear, na, Vidyut? Next one. 15. Let's say we have a capacitor. We have a capacitor, 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 and so on till infinity. It's an infinite grid. This capacitance is C, this is C, this is Kc, this is Kc, this is K square C, this is K square C, and so on. Meaning every time the capacitance is becoming K times multiplication. The standard question is when K is 1. That's a standard question. So this is A and this is B. It's an infinite grid. Find CAB. And whenever you get an infinite grid, we have done something like this in NLM also. I taught you something. Remember this function? Y is equal to root x plus root x plus root x plus root x. This is the inspiration for this problem. How do we approach this? So these are infinite grids. The standard question is when K is 1. How we approach this? हाँ, बैड तो आएगा थोड़ा. It's a quadratic. Let's see. So the idea here is, let's start like this. Let the answer, let C, A, B be equal to X. Now, if you take the whole thing as X, now what we did? So this, if you just remove one branch, this entire circuit is again an infinite grid. This is an infinite branch, or you can say infinite circuit, where C is replaced by Kc. Is that making sense? Initially, when you started, this started with C, Kc, and so on. If you cut the branch here, you'll observe this is starting from Kc, K square C, and so on. So indirectly, it gives you a feeling as if you replace the whole thing with K into C, isn't it? That means the circuit can be written as, so this, if you just remove one branch, you can say this should be K into X. If you replace C with Kc, then X becomes Kx. Is the logic making sense? You are saying let the whole thing be X. And we know X is proportional to C, dimensional analysis. Dimension the match hona chahiye, so there'll be some number into C. Now, if you replace C with Kc, then you'll also get a constant K in front of it. I hope that is making sense. So if the whole thing is X, if you leave one branch, it should be K into X. So this is C and this is C. So CAB should be equivalent of this, which is these two are in parallel, which is Kx plus C. And this are in series. That will be into C by Kx plus C plus C. But we know what is CAB. CAB is nothing but X. The whole thing is again equal to X only. Simplify this. So this would be Kxc plus C square, Kx square plus 2Cx. So we get Kx square plus X into Kc minus 2C plus C square is equal to 0. This is a quadratic. कुछ तो mess up किया मैंने साइन का. This is X into 2C minus Kc minus C square is equal to 0. Therefore, X ka value would be minus B, that is 2C minus Kc plus root over P square. So 2C minus Kc ka square, 4Kc square by 2K. That's your answer. If K is equal to 1, which is the standard question, then X ka value will turn out to be root 5 minus 1 by 2 into C. That was a simplified answer if K is equal to 1. I just modified by putting a K extra there. But did that logic make sense? If the whole thing was X, and you're simply saying the C ka place में put Kc everywhere after leaving one branch, so the whole thing should be Kx. Clear with this? Suppose if I ask you like this, can you tell me how will you do this one? Let's say we have capacitor, 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 capacitor going on till infinity. Then again it comes out. Capacitor, 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 capacitor. Let's say this point is B and this point is A, and the bottom two, I can just call them something like this. All are C. Now, can you tell me what will be CAB? It's an infinite grid in the middle, matlab that side, this side. बीच वाला C नहीं होगा, meaning I didn't get the previous quadratic equation. We had 2C for constant term from right hand side. What you are saying for this? Now here, what we do now, see, let this point be C. I did a mistake here. ये नहीं होगा, this thing. That's what you're saying. It should be a straight line. वो capacitor नहीं है. My mistake. So if you see this entire bottom point now is C only. So this circuit is nothing but, if you just divide into two pieces, this is what you will notice. There is point A, there is one capacitor, and this is point C, there is one capacitor, and this is point B. Now I know the capacitance between C and AC, isn't it? Abhi calculate again, how much is that? Root 5 minus 1 by 2. You getting what we did?
Did you do?
Basically, I'm finding capacitance between A and C. मतलब B को छोड़ दो.
Sure.
That is an infinite grid. Which is how much? Root 5 minus 1 by 2 into C. Similarly, find between B and C. That is another infinite grid. That is also root 5 minus 1 by 2 into C. अभी दोनों को combine करो. Infinity plus infinity is still infinity. You're getting it? So you're connecting between A and C ka one capacitor, B and C ka one capacitor. So the capacitors will look like this, right? So the equivalent will be between A and B. Is the logic making sense? I will find the capacitance between A and C. That will be one full infinite grid. I will find the capacitance between B and C. That will be another infinite grid. Now, if I add these two infinite grids, I will get another infinite grid. Sure. So basically, this is what you did. So this is infinity. You found between A and C. You found between B and C. I know CAC, I know CBC. Now if I join these two, then I'll get CAB. So CAB would be root 5 minus 1. Making sense? You can play like this also. So there are more variations of this. So next class will be quite important. We'll be doing different other kind of symmetries. Axial symmetry, bisector symmetry, and then we have infinite grids. There's still more type of grids. Meaning we will do something like this, meaning there'll be infinite capacitors like this. Each wire is a capacitor. We will do that. Then we will do problems like this. We will do stars. We will do some more symmetries. It's more fun. And then we can also do something like this also. Hexagons. Infinite hexagons. So we will play around all these things. So next class will be more of symmetries. Want it to be root 5 minus 1 by 4 parallel में है ना? You're right, my mistake. सब करके देखो कैसा mistake किया. Clear? So next class when we meet up, we will do more of circuits, more of these things, and then we will slowly transition to the Kirchhoff's law and everything. So mostly we will be doing that in the next class. ठीक है, but I'm telling you this is quite important because whatever I did today and next class we're doing circuits, exact same things we'll do in current. So there we will skip these models, there we'll do something else. ठीक है.